Good morning.
Good morning. So today we'll continue with the time evolution operator, and we have started um, considering it within the position representation. So we'll continue with that, and later we will do the Feynman path integral, which is very much related to this propagator. So in fact, the Feynman path integral is a way of calculating this propagator. So last time we defined the time evolution operator and we computed in the position representations. So we have it here. So I don't know if you can see the lines here, but some reason it does not appear in my iPad, but you can probably see some thin lines there. So it is just the matrix elements of these time evolution operator in the position eigenvectors x and x0. And we have also introduced this theta function here, which indicates that it is a retarded propagator. So it is retarded because the t is later than t0. So one can also define what is called the advanced propagator. So that would be then the theta t0 minus t, where t is less than t0. Then we can interpret this propagator in the position representation as probability amplitude of finding the particle at x at a later time t. So we have an initial state at given by this position eigenvector x0, which correspond to a particle localized at x0, and then this time evolution operator propagates the state to state psi t. So then if we take the overlap of psi t with a position eigenvector x, that will give us the probability amplitude of finding the particle at a later time t. So as I mentioned last week, we have to be a bit careful with the position eigenvector, because if we look at the wave function corresponding to a position eigenvector x, so let's say have x0 here, and we have the state psi, let me just call it psi 0, like that. So then if we look at the wave function, that will be just then a delta function. Centered at x0. But if we compute the square of this is not equal to 1. Yeah, so there is this ambiguity with a normalization. So what one can do perhaps is to think of it in this way. So if this is a delta function, so let's say this is delta here, and the height here is on delta. So delta function would have will look like this if we understand that we take the limit of delta goes to 0. So one way to think about or to circumvent this normalization problem is to introduce a function like this, where the height is defined to be square root of 1 upon the square root of delta. So in this way, then if I call it fx, then fx squared is equal to 1. Yes. So this is just a side remark that so we are aware of the problem with or the ambiguity with the normalization. So when we say probability amplitude, here we have to be aware of this problem. But in practice, we use this propagator in some integral, like what we have here. What am I doing here? Like what we have here. So this problem, of course, does not arise. The problem with the normalization. So here we can see quite explicitly that we start with a wave function psi, and we look at it at position x0 and time t0. Then this propagator evolves the state to state psi at time t and position x. So this is just a position representation of the state. So what I would like to do next is to consider the equation of motion of the propagator. So this equation, this propagator fulfills the equation of motion, as we might expect, because the time evolution operator fulfills the time-dependent Schrödinger equation. So then this propagator should also fulfills Schrödinger equation, time-dependent Schrödinger equation. And you'll see that because of the presence of the delta function, because of the theta function, we will get this delta function here on the right hand side. So if this was 0, that will just be the Schrödinger equation. So let's work out this equation here. So let me start with the Schrödinger equation. So we have p squared to m plus v. So that's our Hamiltonian. Like that. So then if we work in the position representations, we will have psi acting on, let me erase this. Then we just have the Schrödinger equation. What is it? Minus h bar squared upon 2m d2 dx squared plus x acting on a wave function. If this is an eigenstate, then it will be just that. So if we look at the explicit form of the propagator, I think we worked this out last time, so that becomes sum over A, where A is the eigenstates of H. So this is obtained very simply by inserting a complete set of states in between the exponential and the position eigenvector. I think we did this last time. Then we have that one, the theta. Okay. Okay, so now if I, okay, so let me just call this whole thing hx. So now if I operate hx on this propagator, then we see that this is an xa here is an eigenstate of the Hamiltonian. So then that will just give me sum over a x a, and the same thing here. So let me just write it there. Yep. Don't want to repeat this, writing the same thing. So if we look at the time derivative of the propagator, then we will get two terms, one from this exponential and one from the theta function. So now the theta function matters when we look at the equation of motion. So we get sum over a that will bring down the minus ea, but then we multiply by by IH bar on the left hand side. So then we just get EA. This, let me write this quickly. So this is again the same here. I don't want to repeat the same thing. So that's from the exponential term. Then we get also contribution from the theta function. So let me write that down. So we get IH bar sum over A. And now let me write down everything here. Bar. Now, the derivative of theta function, as you know, is a delta function because it looks like this. It's at t0, it is t here, so that's 1. As you can see that if you take the derivative, then the derivative only exists at t0. And then if you integrate this, then you get just 1. So that's the definition of a delta function. Now, because of this delta function, then this term here, this second term, will be 0 unless t is equal to t0. So that means I can just replace that one with 0 because of the delta function. So then this thing here becomes, what do I get here? So that becomes h bar, then sum over a, x a, 0, so that the exponential becomes 1, then I have a delta t minus t0, but this is equal to just h bar delta x minus x0, because that is equal to x0, yes, because of the completeness relation. So we got a nice expression. It's just a delta function. So then we get the equation of motion for the propagator, because we realized that the first term here, this term here, is just the same as this one. So we get finally, hx minus h bar ddt acting on the propagator give me minus h bar d0. So that's the equation of motion for the propagator. So this is in the form of a Green's function. Sometimes it is also called Green's function because you have this delta function characteristic of Green's function. You have the delta functions on the right hand side. So it also has this property that if we take the limit t goes to t0 plus, I will explain what the plus means at the moment. T, that would just give me a delta function. I think you can see this from the definition of the of k. So t0, what am I doing here? Okay, I often have problem with touching things unintentionally. Okay, so t0 plus here means t0 plus some positive infinitesimal, so call it eta. So this is a positive infinitesimal. So I have a question here from me. I think, let's see why we apply the Schrödinger equation to the propagator. Well, I mean, we just want to know the equation of motion of the propagator. So this is the equation of motion of the that is fulfilled by the propagator. Yes. So the we know that the propagator fulfills the time-dependent Schrödinger equation. So then we should see something similar for this propagator, which is indeed the case. I mean, if x is not equal to x0 and t not equal to t0, then this is just a time-dependent Schrödinger equation. Okay, is that
Can you hear me?
yeah.
Okay, because I'm a bit confused as to why isn't the propagator an operator?
Yeah, okay. So we define our propagator. So this is an operator. So I have a hat here divided by h bar. So that's the propagator. And the k is the matrix element of this propagator in the position eigenvectors. Yes. So our k is not an operator. Yes. The k is a function because we take the matrix elements of this U between two position eigenvector x and x0. So it's a number, it's a function. Yes, it's a function, not an operator.
Okay.
Okay.
In that case, I think I understand. Thank you.
Okay, good. Yeah. Thank you. Okay, thank you for the question. Okay, so that's the equation of motion for the propagator. So let's work out an example, an explicit example of how this propagator looks like. Let me erase that. So in the notes, we take an example of free particle. So we look at the free particle propagator. So our Hamiltonian then, of course, is just p squared upon 2m. So you want to work out the explicit form of this propagator. For the case of free particle. So naturally, we will insert a complete set of the momentum eigenstates. So we'll call it P here. P, Px0, and minus P, call it 0. And the EP here is just p squared upon 2m. Okay. So everybody is with me. So this is just the free particle wave function. So that's equal to 1 upon square root of L of the exponential Px upon h bar. So we have chosen this normalization here so that the square of this, so I'm considering a one-dimensional problem. So if I take the square of this, or then this will integrate to 1, yes. So that's a particular choice. So sometimes actually in Sakurai, they use a different normalization because it is normalized in a different way. Yes, so we have to be aware of this. It's just a matter of normalization. So we just have to be consistent which normalization factor we use. We use this 1 upon L, where L is the dimension, the length of the dimension, yes. That will go to infinity. So when we work out equations, the final results should not depend on this L, because L will go to infinity. So L should disappear when we work out any physical quantities. Okay, so now we just use this plane waves in there, so we get 1 upon L sum over P, and then I have, what is it, P then x minus x0, so that's from that term, divided by h bar, and then I have minus ip squared upon 2m t minus t0 divided by h bar, and times the theta function, like this. Now, when we sum over p here, well, p becomes eventually continuous variable. So here we have to introduce what's called the density states. So the density of states in momentum space is given by, this is here maybe. So density of states. Okay, let me write down explicitly. Density of states, sometimes it is abbreviated DOS, in momentum space. So in P is equal to, so this is for the one-dimensional versions, by H bar. Now I have it in the appendix if you want to see how and why it is like that. You can see it in the appendix. I don't remember which one, but you can find it in the appendix if you just look at the indexed content. So that is based on the kind of periodic boundary condition. So we have that. So we can turn this summation into then, sorry, not that one, but just this one here. So this summation can be turned into an integral over dp like this. Yes, multiplied by the density of states dp. Okay, so there's a bit of algebra here. There's a lot of constants all over the place. So I don't want to go through all this algebra here, but I would like to just describe how we proceed with this exponential here. So we notice that this is in the form of a quadratic function in P. So if we look at the numerator, this exponential. So just look at the exponential, it will be of this form. So we have minus I and then some constant AP plus say VP squared, like that. Okay, but A and P are constants. So for example, A will be equal to minus x0 divided by h bar. So I just got it like that. So this can then be written in the quadratic form. So the idea is that to write it in a quadratic form. So we get p plus some constant c squared, and then we subtract minus bc squared. So if we do that, then this expression becomes what we get in the notes there. Okay, so let me just write it down. So we get 1 upon L an exponential x minus x0 squared to 0. Let me write this down completely. It's just algebra here. It's nothing difficult. Zero x minus x0. Let me see. Have a squared like that times the theta. So we see that this thing here corresponds to the bc squared term, and this thing here, then just that one. So we form a square of that. So if we do that, then we can use the standard formula for the Gaussian integral, because it is now in the form of a Gaussian in P. It's just that it is centered at this point here. So then we can do the integral analytically. And let me just write down the result here. Because the result is a bit interesting. And I have this also in the notes, of course. Easier. So that the explicit expression for the propagator of a free particle. Now, if we take the square of this, because this is supposed to be probability amplitude, so you want to know the probability, keeping in mind that we have this normalization issue. But, so we have to keep that in mind, that we should not interpret this as the real probability, but something proportional to the probability. Then we see that it is proportional to t minus t0. So that is consistent with what we found before, that if we have a particle localized at x0 in time t0, then it will eventually spread as time passes. Yes. So this is consistent with what we had before when we work out the commutator between delta x at time t and delta x at time 0. So you see that the probability at a given point x will decrease with time because it's proportional to 1 upon t. So then it means that the particle will spread if it is initially localized at x0. Okay, so let's look at the Fourier transform of the propagator. So the propagator has an important property in that if we analyze the spectrum, that is to say the Fourier transform of the propagator, the poles, so it turns out that the Fourier transform has poles in complex plane, will correspond to the excitation or the eigenstates of the system. And this is an exact result of the propagator. So before we do that, we should know how to represent the theta function. So we call it t minus t0. We should know how to represent the theta function in terms of an integral. So this is an integral representation of the theta function. So we are now going to a complex plane. And we need to use Cauchy theorem. Like that. So how do we know that this integral is equal to theta function? So let's have a look at the case when the tau is positive. So then, since this is an integral in a complex plane, and this is from minus infinity to infinity here, this is what we want to do. we can choose a contour any way we like, but we choose the one which is suitable for our problem. So we say that there is a pole. There's a pole at omega equal to eta. There's a pole here. This is 0 here. So this is our omega here. So a simple contour to do this integral is just a kind of semicircle like this. Yes. So for t positive. So if we take any point here, so that we can write as real part plus imaginary part. So we have to keep in mind that this is infinity here. It's minus infinity. So, well, it's a very large semicircle. Yes. So then, if we look at the exponential, omega tau, so that's equal to ei omega r t, the real part, and then we have e to the minus omega I tau. So both omega I and tau are positive. So then when omega I becomes very large, so any point here on the semicircle is infinite. It's very large because we have a very large semicircle. So as soon as we are away from the real axis, then omega I becomes infinite. Yes. So then this goes to 0, this thing here goes to 0. So that is a kind of converging factor to do this integral. So this means that according to Cauchy's theorem, we have this integral then equal to just the residue. So 2 pi I times the residue. And the residue, so there's a 2 pi I here, so that the 2 pi I is divided again by 2 pi I here. So the residue is just, okay, maybe I'm confusing you with this 2 pi I. So without the 2 pi I, then it will be just 2 pi I times residue. But because I have already included the factor of 2 pi I, then we just get the residue here. So the residue here, it can just e to the I times eta tau. So that is to the minus tau. So eta is again the positive infinitesimal. Infinitesimal. Now, if tau is negative, and then we close the contour in the lower half plane. So let me just sketch it here. So for tau less than 0, we close the contour in the lower half plane like this. Yeah. So there is no pole in this semicircle because the pole is up here. So then the integral is just 0. So that fits with the definition of theta function. So when tau is positive, it should be equal to 1 because the theta function looks like this. This is tau here is 1. When tau is positive, is equal to 1. This is 1 in the limit of eta goes to 0. So we always understand that eta is supposed to be taken to be 0. So it's a limit of tau goes to 0. So that goes to 1 here. And When tau is negative, then it is 0. So that is what we get here, what we have here. So I also have the this Cauchy theorem in the appendix if you have forgotten about it. So we use this again later in the in scattering theory. So it's good to know what this, how to do this kind of integrals in the complex plane. Yes. So that's the math. So now we want to do the Fourier transforms. So we take the Fourier transform of the propagator. That is just tau, so I'm using this variable tau times the k, which is given by sum over eigenstates of the Hamiltonian. So this is not restricted to free particle, this is quite general. So this A is not free particle eigenstates, but just any Hamiltonian by h bar times tau, like that. So now I can replace this tau with this tau like that. So we have sum over A x0, so that doesn't have any dependence on tau. And because of the theta functions, the integral is limited now from 0 to infinity. And we have the tau. Now I'm collecting the exponential. So I get omega minus, and this should be EA here. EA plus, let me see. I somehow there's a mistake maybe with a factor of h bar here because I defined omega without the h bar there. Okay, so let me come back to that later. I just noticed a little typos there. So this becomes plus tau divided by h bar. So I have replaced the theta function with this. Yeah. So then, so this should be h bar here. There should be an h bar here. Okay. Because I divided by h bar. Okay. So then, if I do this integral, it's just an exponential. Then we get a nice expression for the propagator. Plus I eta. So eta is infinitesimal, so you can always multiply by some constant. It doesn't make any difference. So we should think of eta as kind of undefined constant. It's just to indicate that something is positive. Yes. So if I multiply this by h bar, well, this is just equal to just another infinitesimal. Yeah. So it's a bit like infinity. If I multiply infinity by constant, I get another infinity. It is something like this. So this is our expression for the k propagator. So we notice that it has poles. It is so here, so you multiply that by h bar. It has pole at the eigenenergies of the Hamiltonian. So this is called the spectral representation of the propagator. Poles of k correspond to eigenvalues of h of the Hamiltonian. Okay, let me look at the time. Okay, we are going over the time there, so maybe it's a good time to stop here. Have a little break and can meet again at a quarter past. Okay, so let's continue. Hope everybody's back. Okay, so we just derived an expression for the retarded propagator, the spectral representation of it, and we found that poles of these propagator actually gives us the eigenvalues of which. Now, of course, if we diagonalize the Hamiltonian and we know the eigenfunctions, then this is not a particularly useful result. But the point is that there may be other ways of computing the propagator without explicitly diagonalizing the Hamiltonians, without explicitly finding the eigenstates and the eigenvalues of the Hamiltonian. If we could do that, then we know that if we take the poles, we consider the poles of this propagator, that will give us the eigenvalues of the Hamiltonian. So let's have a look at this propagator in more detail. So if we consider the trace of this propagator multiplied by I, as we have here, this is just a definition. So we take 1 upon pi times the imaginary part of I times the propagator and takes the trace. And we see that that is equal to a set of delta functions centered at the eigenvalues. That we can easily see because we take the trace, then we get the square of the eigenfunctions, and when we integrate over the space, that just give me 1, because eigenstates are normalized to 1. So this is one thing that we should also know, that if we have an expression like 1 divided by x plus I times an infinitesimal, and take the imaginary part of that, that is actually equal or proportional to delta function. Yes. So we say that this expression here is equal to minus eta divided by x squared plus eta squared. So if we take the limit of eta goes to 0, that is just a delta function. So the integral of eta divided by x squared plus eta squared is equal to pi. So this could be a good exercise to do the Cauchy, to use the Cauchy theorem here. So one simple way of doing this would be to go to the complex plane and write it as x plus I eta, then x minus I eta. So it has two poles, one above this and one below the relaxes. Right? So this integral is of course from minus infinity to infinity. So then again we can close the contour like this. It doesn't matter whether we close it above or below, we should get the same result like that. So the integral along this curve here is 0. So along this semicircle, the integral is 0 because it goes like 1 upon x squared. So it's important that the power is bigger than 1. is x squared, and so that's bigger than 1 upon x squared. So then it has no contribution. So then according to Cauchy's theorem, then we just get 2 pi I times the residue. And this residue is just eta divided by 2I eta. So then we get pi. Yes, that's one way of doing this integral. We can also close the contour downward like this, and we get the same result. Yes, we can also do it like that because the integral here is also 0 along the large semicircle. So this is infinite. This minus infinity here. So we get the same result. Yes. So then, if I take the imaginary part of this expression here, so that would be just pi times this delta function. So we see that the imaginary part of this ik divided by pi gives us a series of delta functions centered at the eigenvalues of the Hamiltonian. So in other words, that's just the poles of the propagator. So that's the very general properties of this propagator. And it's also it's a very useful property, especially when one does many particle systems. One could also define a propagator for many particle systems, and it has the same properties that the poles of the propagator gives us the kind of excitation energies of the system. Okay, so now we can start doing path integral. Yeah, so we have a Feynman path integral. So we want to find a way of computing this propagator. So that's the definition of the propagator. This is just a little remark here that I can also think of this in the Heisenberg picture. So in that case, I can define the state xt, which is a kind of reverse state from time t to time 0. So that's why I have a plus iht divided by h bar instead of minus, because the minus will propagate the state forward, whereas plus would propagate the state backward in time. So that then gives me the Heisenberg states here. So the idea of the Feynman path integral, as you might already know, is to split these matrix elements into many segments in time, and then find an expression for each segment, and then do the integral over all the segments. So let's do that. So the idea of the Feynman path integral. Maybe before I do that, I should talk a little bit about the classical version of this. In Lagrangian mechanics, we think of the motion of a particle from one point to another in terms of action, functional. So we say that we have some action, which is an integral, let's say from time t0 to time tn, So I put n there to indicate later that we will split the path into n segments. So I have a Lagrangian, which is a function of x and x dot, where x is some canonical what do you say, variable or whatever. So L is the Lagrangian. So this is equal to the kinetic energy minus the potential energy. Then the Lagrangian mechanics tells us that if we minimize these actions, this is the action here, subject to the boundary conditions that we start from time t0 and its position x0, let's say, and time tn at another position xn, then the path that the particle takes will be given by the least action. So actually it doesn't have to be the minimum, it can also be the maximum. So it's the extremum of the action, but it's usually called the least action. So we say then ds, so we make a little variation of d, then that is equal to 0. So this is the principle of least action. So if it is a minimum, then it looks like nature is a bit lazy, so it does the least action. So if you are positively minded, you can say it's economical, since nature takes the least action. So if we do this, then we get, we'll not derive it here, but just remind you what you have in the Lagrangian mechanics. You have this Lagrange equation of motion. Sorry, this is not dt, but dx. Should be dx plus. So these are just equivalent to Newton's equation of motion. Yes. So this is equivalent to force, mass, time, acceleration. Yeah. So it's a rather beautiful way of looking at the mechanics of motion of particles. Since the motion is governed by a very simple principle that you just minimize the action from one point to another. Now, in the quantum mechanics, then we also have kind of a corresponding concept, which is the Feynman path integral. So the fundamental difference is that instead of just taking one path, just given by this least action, that would be the classical path, we have instead to consider all the possible paths in going from this point to that point, from x0 t0 to xn tn. So we have to consider many different paths here in quantum mechanics. And also we have to look at probability amplitude. So this is where the propagator comes in. So let's see how we can formulate this in a more precise way. So let's look at K, propagator. So that is given by Tn x0 t0. So we just started the definition of the propagator. So we can also write this, which is using the Heisenberg state. So this is the overlap of two Heisenberg states, like that. So now we introduce a time in between t0 and tn. So let's call it t1. So we split this propagator exponential to the minus h times the time the following way. So we write this h bar tn minus t1. So we introduce new type t1. So okay, so we haven't done anything because I have this t1 term, so we'll just cancel. This one is plus and the other one is minus. So we haven't really done anything. But we can now introduce a complete set of states here. We can introduce, call it x1, so like that, and integrate over the x1. So then this becomes integral to x1 and tn t1 x0 t0. So we have introduced one time in between t0 and tn, but in principle we can introduce as many time steps as we like. So if we introduce, let's say, n time intervals, so we'll have delta t, let's say, is of equal space by n. So that would be time difference between two neighboring time elements or time segments. Then it is easy to see that we can write the propagator as what is known as path integral. x1 like that. So we introduce n minus 1 times in between x0 and t0 and tn. So let me write a few terms here. So 1, and then we get eventually x1 t1 x0 t0 at the end. Okay. So this seems to be quite straightforward. Just introduce types in between, and we let them and as many as we like. Now the problem though is how do we calculate this integrals here? So the main task, the main problem is to compute these matrix elements between the Heisenberg state x and tn and the neighboring one. Like that. So what is this matrix element. So we know this, then we can compute the propagator as the sum over all the possible paths. So maybe I should show you the thing here. Okay. So we want to determine this matrix elements. So according to Dirac, this is a Dirac postulate. This is given by the following result. Let me make sure I get the right expression here. So this S here is classical action. The action that we had earlier. So that is minus from Tn minus 1 to Tn integrated over time of the Lagrangian. Yes. Like that. So we write it in discretized form, that will be delta t. So that delta t becomes just dt just become delta t, because we are looking at a finite time difference, no? And we understand that the delta t will be made as small as we like. Squared, so that's from the x dot. And then I have x. We can compute this at a kind of average position between xn and xn minus 1. And omega here, and not omega, it should be w here, small w, it's just some weight. So omega is just some weight. So done this correctly, then we would find that this thing is equal to the square root of m divided by 2 pi I h bar delta t. So this is according to Dirac. This is Dirac here. Dirac postulate. Since we are not Dirac, so maybe we want to understand a little bit better why we get this form here. So we'll do it in a more explicit way. So try to kind of derive this expression here. And there are several methods of doing this. So one way is to do the following. So we want to compute this matrix. Let me write this down. That's one. So delta here is just Tn minus 1. So we do this in a more down-to-earth fashion, you might say. So we just make a Taylor expansion. So we have this as h bar h. So h is I shouldn't have that here. So it's put the operator in the p and the x. Delta t. plus some higher order. Term in delta t. So let's see what happens if we do this, and we get a little bit of space here. So we get 1 minus h bar x delta t, and then x n minus 1. So we forget about the higher order term. Because we can choose delta t as small as we like. So now we use expression for the Hamiltonian. So that is e squared 2m plus some potential. So the operator is on the p and the x. T minus 1, like that. Now, the xn and xn minus 1 are eigenvectors of the x operator. So we can just replace this one here with either xn or xn minus 1, depending on whether we active to the left or to the right. And the problem is not how to compute the matrix elements of this momentum squared, p squared, because xn and xn minus 1 are not the eigenstates of the momentum operator. So what we do is just insert a complete set of momentum eigenstates. So we write, maybe I can just continue here. So that can be written as L by h bar. So that's the density of states in momentum space. So now insert p here. So these are the eigenstates of the momentum operator. Then I have an h bar p squared m plus xn minus 1, like that, times delta t. Nice one. Okay, so now we can operate this this kinetic energy p squared to the left. That gives me the eigenvalue. So I can just remove the hat. Just remove the hat there. Okay. So then this whole thing is now a number. So I can take it out from the matrix element. So that becomes h bar integral dp. Then I have x and p. So that's the plane wave minus 1. So now I can put back these this number here. an exponential, so I can write it as p squared plus 2m plus p minus 1 delta t divided by h bar. Okay, so this is correct also to first order, because we're only looking at the terms to first order in delta t. So I can write it like that. And this thing here, x and px minus 1 are just plain waves. So we get, so let me write it here. So x and p is just equal to I and divided by h bar divided by square root of L. So then the L disappears as it should be. So when we do calculations, we should in the end get rid of this factor L. So if the factor L remains, that indicates that we have done something wrong with the algebra. So then this becomes dp divided by h bar, and I have p x minus 1 divided by h bar, and then we get yeah, it's the same thing. Should have just minus 1 here. Okay, so we have this integral over p with the momentum, which is a Gaussian integral. So this can be done analytically, like we did before. So if we do that Gaussian integral, we find that I have this derivations in the appendix, actually, so you can have a look later if you miss the details here. Delta t. And then we get this after doing the integral over p, the momentum. So divided by delta t squared minus p n minus 1. Okay. So that's exactly what the Dirac postulate says. So that is then the weight, and these are just the Lagrangian. Yeah, that's the Lagrangian. So that's one way of deriving this propagator between two neighboring time elements. So if we put things together, if we insert now to the expressions that we get for the path integral, then we have the following. So we now take the limit n goes to infinity. We divide the time intervals over many segments. delta t like that, upon 2 because of the square root. And then I have an integral over the position from xn minus 1 to x1 of the, is the same thing here. But now I have to sum over n from 1 to small n, 1 to n of the Lagrangian. So the potential is calculated at xn minus 1, but we could have taken the average, yes, because you can act to the left or to the right, so it's not so important. After all, we will let delta t goes to 0 in the end. So this integral is sometimes written in a shorthand in this way, just to n, and call it d to represent this x d and dy. So this is just a shorthand, yes. Bar integral from t0 to n dt Lagrangian x dot like that, and these are just the action associated with a particular path xt. So this d here is just the whole thing here. It's the measure of the integrals. So that is basically what is called path integral. Path integral formulation of propagator quantum mechanics. Now, one way of visualizing this path integral is a rather famous picture you can find in many textbooks and many other places. So this is kind of pictorial representation of Feynman path integral. So we have 2 points, x0, t0, and another xn, tn. Then as I have written before, that you can then split the time here. The y-axis is the time, and the horizontal axis is the position. So when we insert the complete set of position eigenstates, so we are referring to this line here, for example. So we integrate over that x. So we have to consider all possible paths in going from one point to another, not just one path. That what we have in what we have in Lagrangian mechanics or classical mechanics. So sometimes we can interpret this quantum mechanical path as being concentrated on the classical path. So we have one particular path like this, and the quantum mechanical path that is most important would be kind of close to the classical paths, depending on how quantum mechanical the system is. So in the limit of classical action, so we're looking at the classical limit, and we can understand this picture of summing over the various paths as being the summing important paths that are close to the classical paths, close paths. So the Feynman path integral recently has found a lot of real applications in studying quantum systems. So it has become kind of standard method of making quantum simulations, especially when we have many particles in the system. It is virtually impossible to work with a Schrödinger equation and try to diagonalize Hamiltonian when the number of particles increases. So we can maybe handle tens or maybe 100 particles and diagonalize Hamiltonian. But when the number of particles increases to some Avogadro's number, then it is virtually impossible to diagonalize Hamiltonian. And the path integral here provides a different way of handling its problems. So one can calculate the propagator, and as we have shown before, that from the propagator you can deduce the excitation energies of the system. There are different ways of calculating the Feynman path integral in practice. So we will not go into that here. But the final thing I would like to say is that we can show, I think we have actually already shown this, that the propagator fulfills the Schrödinger equation. So we have shown this from the definition of the propagator. We will not go into it here, but you can easily also check that the path integral formula, that is to say this one here, this one here, this one, let's say, also fulfills the Schrödinger equation. So this formula is correct because it is equivalent to the time-dependent Schrödinger equation. Okay, so maybe this is a good time to stop and can continue next time with the gauge formation. So maybe you have some questions up to here. Yeah, so as I said before, this derivation of the Dirac postulate can be found in the appendix. Okay, so if there is no questions, then we stop here and say goodbye.
Bye-bye.
Bye-bye.
Thank you.
Thank you. Bye-bye.
Have a nice day.
You too.
Thanks. Bye.
Bye, everybody.